So, hello, welcome to the colloquium of Iparcos. Okay, panic? Okay, no panic. So, it is a very pleasure today to have Abhay Despande from Stony, Brook and Brookhaven National Lab. He's actually director of a new experiment which is going to be built in Brookhaven, which is called Electron Collider. As any new adventure, it's full of possibilities, full of new things to discover, and full of physics. That's why we are here. And Abhay has been director of the EAC project in Brookhaven for quite a few years. And actually, he's really doing a great job there.
Remote.
And one of his purposes is to attract students, postdoc, researchers in general, to the physics of EAC. And then to the potential implications of the discoveries that can be done in this new accelerator. So he will tell us about all this in his colloquium, which is actually open to all students and so on. We are very happy and honored to have him here and to visit Spain and Madrid. So, well, I'll leave him with the duty.
Okay, thank you very much.
Thanks a lot.
Thank you, thank you. This talk is for all of those people there. This experiment and the collider is going to run in about 10 years, right? And we want you. So think about it, that potentially this might be a place where you can work. Yeah, we all will be old. She will be leading. She already knows everything about it, so, okay. So I'm delighted to be here in Madrid. I've been here for meetings in the past, but only short time, and this time there was just a nice opportunity to spend some quality time looking at your beautiful city, attending, visiting some museums, and having some wonderful food. And so I'm glad that this was finally come through. So I'm delighted to be here. What I'm going to tell you about is about this new collider called the Electron Ion Collider, which is just about to be beginning to be built at Brookhaven National Lab. And I'm going to give you an example of what science we will be doing during that time. The condition that he gave me was there will be no single equation in the entire talk. And I have taken 2 exceptions. But those exceptions are simple enough, I think. Even I could understand, so I'm sure you will. Yeah? So, another title for this talk, a physics-oriented title, is to understand the role of gluons. I call it the super God particle. You know, the God particle is the Higgs particle, imparted mass to everything that we see, we think. But I'm going to call this super God particle for a reason, and I'll come back to this a little later in the talk. So we all have been extremely, yeah, you want to?
It's all right,
No. Oh, wonderful. Thank you. We're all very curious about nature. We want to understand how we are built in fundamental particles. I have to come close, I think. So here we see a droplet of water, and we know that it is made up of molecules. And the molecule has H2O, so there is 2 hydrogens, 1 oxygen. If we look into the atom, we know that there is a nucleus surrounded by the electrons. We know already for a long time, about 100 years, what the electron properties are. It's negatively charged. It has a spin half. And it is, as far as we know, unbreakable. It is a point particle. We know that they go around the nucleus. The nucleus size is much, much smaller than the shown here in this cartoon. And then there is the nucleus, which is made up of protons and neutrons, which is positively and neutral particles. Go down one step, protons and neutrons we know are made up of quarks. Since about 1968, we know that those are made up of quarks, and they're bound together very strongly with something called the gluons. And that is shown in this cartoon here, that there are quarks bound by these wiggly little particles that are sitting there, which are called the gluons. And that's all we know about the fundamental structure We also know that the quarks are spin half particles. They're fermions like the electrons. But they have a different type of charge. In addition to the electric charge, they have a fractional electric charge as well as color charge. And the color charge is the strong charge that is essential to impart the properties of the strong force. So the interactions of the gluons are between color charge particles that are inside the proton. You can think that color charge has to be very strong. Why? Because these quarks can be positively and negatively charged, fractionally charged, I'll come back to that. But if you take two charges, two protons, or two quarks, which are positively charged, and you want to try to put them inside the proton, which are of the order of 10 to the minus 15 centimeters, then you have to overcome the repulsion between them with extremely strong force. Something has to be overcoming that extremely strong repulsion, and that comes from these gluons that bind the quarks together. We understand that is the essential aspect of the strong force. And that's where some of the background information comes in. So how do we know all of this? So there is a technique. There is a tool that has been used historically by every scientist in the world to understand what is the smaller and smaller particle. So what is the principle behind it? The principle behind it is that we need to get to higher and higher resolution. So what is resolution? People want to clarify what a resolution is, and here is a cartoon of that. What is the smallest size of our instrument, an observation? That's called the resolution. The higher the resolution, the better we see and recognize objects of interest. Yes? That's the principle. Now I have this something there which looks like a vertical thing. Can you guess what it is? Yeah, he knows that I came from the US, he's biased, and he gave me the answer, right? The Statue of Liberty, correct. But it's difficult, you were guessing as to why, right? Be honest, you did not guess that, right? But I increase the resolution, and there you go. You can start seeing the Statue of Liberty more and more. If this works, yes, this works, and now you know that it's Statue of Liberty, for sure. Remember this, because I'm going to use this again and again. So here is what we are trying to do. We are trying, with this one here, a simple microscope, where we use a wavelength of light, visible light, which is about 380 to 740 nanometers, that gives us a resolution of better than 200 nanometers. If you go to an electron microscope, the wavelength that we use is of the order of 0.002 nanometers. You see, much smaller than that. That's a 100 keV electron, and the resolution is about 0.2 nanometers. So now we have reduced the resolution to go look at smaller things, and that's why the electron microscopes now is able to see smaller things than the normal microscope. If I jump to an accelerator, a particle physicist or nuclear physicist now are accelerating the electron beam to 20 GeV. In this case, remember this was 100 keV. Now I'm going to 20 GeV, giga electron volts. Suddenly the wavelength is much smaller, 0.01 femtometer compared to this, and now you have a resolution of 0.1 femtometers. Yes? So now I'm able to see any object of that small size. Now the atomic nucleus of the proton is a few femtons, or femtometers. So if you see a 1/10 of it, I know I'm able to see inside the proton. That is the idea. We want to see something. We want to see the structure inside. I want to have a wavelength which is smaller than the size of the object that we want to see. That's the fundamental rule. Yes? Our friends at CMS, at high energy, they have multi-TeV beams. So the probing structures are extremely high energy. Yes? Extremely high energy, extremely high momentum, which means that the wavelength must be extremely small, much smaller than this. And why do they want to do this? Because they are looking for the substructure, physics beyond the standard model for quarks, for example. And that's why you need the highest energy, smallest wavelength. What we are trying to do in this project is not to go for highest energy, to go to highest wavelength, but to get to a size which sees a collectively large part of the proton or the nucleus together. to see how quarks and gluons, when they come together, what is their interaction together is what we are looking for. So this is the wavelength we want. Yes, this is the wavelength approximately we want. We don't want the highest energy, but we need a lot of it. So I'll come back to that a little later. So that's the focus. So this is the basic principle, the lambda, the wavelength which we are going to see is just h bar divided by the momentum. The larger the momentum, the smaller the wavelength, and you can go inside. Yes, you all want to do is to go inside the proton. So that's the basic. So what do we know? These kind of experiments have happened over the last 50 to 70 years. Accelerated physics experiments, either electron scattering, muon scattering, or proton scattering, whatever it is. Each one of them, as you know, has a wavelength associated with it. Once you have a momentum of a particle, you know what the wavelength is by that simple formula. And then you can explore the appropriate wavelengths or distance scales. So what do we know? So we know what we call today the standard model. The standard model consists of 6 types of quarks, and the gluons that interact with these, with the color force or the strong force that I described to you. We have the weak sector here, the neutral leptons and the charged leptons. And then these are the forces, all of them, the gluon, the photon, electromagnetic, and this is the weak forces, and the last one, which was discovered, the Higgs boson, in 2012. Some of you were all authors on this paper, and that's what is the origin of mass, as I told you in the past. And most of these discoveries have achieved lots of recognition in terms of Nobel Prizes, et cetera, et cetera. Now, we are going to focus today on the interactions of gluons and focus something about how quarks are held together. So that's the basic idea, and we're going to do that, come back to that a little later. Until about 1970s or 80s, our ideas about what a proton is made up of was simplistic, because we knew the properties of the quarks. Yes, 80s, we knew the properties of the quarks. They spin half particles, their charge was fractional, we knew that. So if you want to build a proton which has a positive charge, single electric charge, and the spin of a half, you could simply make a model that says the spin is half plus, and minus half. So basically the U quark and U quarks are spinning that way, the D quark is spinning that way, and that gets you the proton spin half. The charge-wise, it's 2/3 plus 2/3 minus 1/3, and then you get a proton. That was a simple idea. The idea worked, because I can do the same thing with a neutron, and the neutron comes out to be minus 1/3 plus 1/3, the spin is half, and then the charge becomes 2/3 minus 1/3 minus 1/3. Simple idea. Works. Everything works. People who did calculations and models at that time actually did everything right. The pions, similarly, pi plus, the spin is 0, the charge is 2/3 plus 1/3, but it's UD bar, and then you have the charge. Similarly for pi minus, and we understood that as well in terms of this simple model of quarks. Gluons were not necessary. We didn't appreciate the value of gluons at that point. This was before QCD was accepted or even published. Yes, 70s or 1970s was the time. So this was the transition time from our understanding of electroweak in QCD and then discovering the strong interactions, really understanding them. So everything worked, so people didn't think too much about the gluons at all. But they were important. So now we know that that's not true. However, now let's look at it backwards and see what's the basic difference between QCD and QED. And 3 lines that tells you that what distinguishes between QCD and QED is the color dynamics, and the electrodynamics, the difference between them. The first thing you know, the gluons and photons, the carriers of color are the strong forces, and they are the electromagnetic force. Both are massless. No mass to anyone, 0 mass. Gluons carry color. That is the fundamental difference. The photons are chargeless, 0 charge, whereas the gluons carry color. One of those 3 colors, they do have it, which means that they can interact with another gluon of a different color. That is the fundamental difference. You can never see a photon interact with another photon the way the gluons can interact. There is self-interaction because of the color-carrying nature. There is no self-interaction in photon interactions. What it means is the photon-photon interaction is not possible. Gluon-gluon interaction is abundant. That fundamental difference between the electroweak and strong theory makes all the difference in the world. Let's look at those differences. So on the left-hand side, you see a diagram in which a gluon is splitting into two, and that two can be either two quarks, a quark and antiquark, or they can be charged particles. On the right-hand side is only gluons splitting into two gluons because they can be of different color. Remember, gluon-gluon can interact because they have two different colors. They carry colors. Fourth interaction also happens. So in the electromagnetic sector, the photon can split into quark-antiquark pairs or electron-positron pairs. But a diagram like this with photons only can never be possible. Can never be possible, yes? And that is the fundamental difference between these two. And that has huge consequences. To measure this, let me just give you an example. So you take you know what a Gedanken experiment is, right? Thinking experiment. Einstein used to do that. Think about it. Actually, don't do the experiment. I want you to think with me. You take an electron from infinity, and you bring it to your lab, and you stop it. What all will happen in that process? You have an electron starting, it's a charged particle. You know that when it starts moving, it starts radiating energy. Then you stop it in your lab. It means that it will give out all the energy by radiation, and then when it is stationary, it will form a static electromagnetic force or field around it, and that's it. Now you think about the same thing with the quark. You move a quark from infinity to your lab and you stop it. What will happen? Will it be as stable as the condition as the electron? No, because what happens, you reduce the velocity of the quark. That means it's radiating now, this time gluons, as well as photons, but that's a different thing. In this case, it's radiating gluons. But each gluon that radiates will create 2, 3, 4, because of that interaction, glue-glue interaction. Each double will create a 4. 4 will create 8. 8 will create 16. This process can never stop as long as the next level of gluons are at a lower momentum. Yes? Energy is conserved, but the momentum can be smaller and smaller. So the number density of the gluons can grow infinitely in this case. In fact, I will come back to this. This is mentioned in one of the Nobel lectures, that a color charge in isolation can become a thundercloud of color. That's different. It never happens in electrodynamics. Completely different experience than you and I have in all normal life. Yeah? And this will come back as one of the important measuring things in the deep inelastic technique that we're going to use. So why am I going to hit the electron with the proton or electron with the nucleus? Well, it's called deep inelastic scattering because I want to use a wavelength to go inside. The wavelength has to be smaller than the size of the proton or the nucleus, and want to see inside of the proton. So scattering of protons on protons is like colliding Swiss watches to find out how they are built. It was a famous quote from Richard Feynman. Yeah? I argue that it is slightly overspecious to say what is there, but not how they work. Once you break the proton, you don't know how it works. Yes? Think about it, yeah? And I will use this later again. So I would like to modify this a little bit for the reason why I'm going to use it slightly differently. So this is what happens. This is what happens at RIC, at LHC. You see the tunnels of RIC, tunnels of LHC, and a large collision, energy collision happens between particles. Proton-proton, nucleus-nucleus, and the tracks come out and you know how to analyze them and look at them, yes? What is different about what we plan to do in DIS in the future is like the study of watermelons. If I want to ask you, what is the structure of the watermelon? You can do this experiment that you've been doing. You take two watermelons at high energy and bang them, and all the things come down. You can tell me based on this that the watermelon is formed of seeds and the meat. But I won't be able to get an answer from you if I ask you what was the distribution of seeds inside the watermelon in X, Y, and Z direction. You won't be able to tell me definitively from this experiment. For that, you need a different type of experiment where you have a knife that hits the watermelon at a controlled angle in a controlled way. The knife is unbreakable. The watermelon has a structure. So when you see the parts of it coming out, you know that the parts are coming out of the watermelon. That's what we are going to do with the electron-proton scattering. Electron is the knife. It's completely unbreakable, and I want to measure it exactly under control. And that's what the method I'm going to be using. The knife is the electron, scatters off, exchanges a photon of a momentum q with a lambda, has to be smaller than the size of the proton or the nucleus, or here in the case of the watermelon, and I'm going to make the detector such that we see everything else. We also measure the flying electron. Yeah? You're with me now, right? That's the difference. We're going to do this with care and control. I can control the electron well to do this. Okay, let's go to the next one. So now the mischievous gluon, or the super God particle. As I mentioned in the proton mass puzzle, these two got the Nobel Prize for it, understandably and arguably correctly so. The Higgs boson gives masses to all the fundamental particles in the standard model. True. Neutrinos are sort of special, we don't know yet, but quarks and leptons, yes, they give mass to that. Then you say, if I just weigh the quark masses of a proton, you get about 10 to the minus 26 times 2. But in this unit, the exact mass of the proton is about 100 times larger. That's like saying 1 plus 1 plus 1 is equal to 300. Yeah? Because it's like 1% of the total mass of the proton, and that has to be something of a problem. That means that protons and neutrons, the quark and the gluons together, constitute only 1% of the mass, whereas the actual mass is coming from the interactions of the gluons and quarks. The energy of interaction inside the proton through E is equal to mc squared is giving the entire mass to the proton and the neutron. But you know that the protons and neutrons are fundamental particles of everything that we see in nature, which means that we have not explored 99% of the observable mass of the universe. Yes, this is not a small problem. And how do we get there? How do we see inside the proton to figure this out? It's something that we will want to do. It's the rest of the mass has to come from those interactions. This is not a very simple thing, and it results in a very interesting fact. On the left-hand side is a cesium atom. And these days, people are using that interaction, electromagnetic interactions, because we know them so precisely, to define what 1 second is. And the current accuracy is 1 second in 222 million years. If I today build a clock using our knowledge of the internal structure of the proton with similar assumption, it comes out to be 20 minutes and an hour. So it's 30%. It's that bad of an instance. Considering the fact that we know the existence of the proton and the electromagnetic structure for approximately 100 years, we have not done well in understanding the proton. And the reason behind this is the interactions with the gluons. Those are the ones you cannot calculate, because every time you stop your calculation, to give you an example, the gluon will split into 2. Then it will split into 4. Then you do another extrapolation to get to those, and those small will do the same thing. And that is the problem. That's why the calculations have to be done under same difficult conditions. The theorists are very difficult. So you cannot predict outside of the region that you have experimentally measured. So you have to measure it and then go to the theorist and work with them to see how we can see it. Yeah? That's the beautiful part of working in this field. So now I want to step about and show you that spin. I talked about large number of gluons. Now I'm going to show you a clip. And the idea behind showing this clip is it's nothing to do with QCD. Well, it is made up of particles which are made up of QCD, but so have you seen a levitating top? No? Now you're going to see one. This is my office at Stony Brook. It has gravity in it, for sure, I know. Gravitational field exists. There's a plastic top with a metal ring on it. And there is some magnet here, the direction and orientation of which is a homework for you to figure out. And I just spinned it, and it goes, levitating. Now, you know magnetic fields, you know electric fields, you know gravity, you know rotation. You've done first year rotation, right? Introductory physics. If you know all those four things and the properties of the metal, you should be able to figure this out. But it's not as obvious, even if you know all of them very well, as long as there is orbital angular momentum, rotation, things become very interesting. There's only one solution to solve it if you take care of the orbital angular momentum in this picture well. Otherwise, you cannot solve this problem. Yeah? And that's the thing that people have seen, that at the end of this clip, the frictional forces in the air became so high, the rotation stopped, and then the drop fell. Until then, it was working against gravity. Yes, it was able to work against gravity for its weight. So you have to think about all of those things to figure out what was going on and figure out the orientation of the magnet. Yeah, it's non-trivial. The reason why the idea behind showing you this is that spin brings in interesting things. The proton has spin. The quarks have spin. They're interacting with each other. That means that they are creating things inside them which are not quite understood, but once we understand it, we'll understand the properties of the proton. So the idea is to understand spin to understand that. So the experiment we did at CERN in the 1980s was a simple one. You took a proton, which is polarized this way, means it's put in a magnet. We know the proton has a spin half. It's oriented in one direction. Now, in the previous picture, when I said the proton spin comes from the alignment of the quarks, remember that? I said in the beginning. It comes from the alignment of the quark, and it works for all the models, proton, neutron, pion, and kaon, and anything. And so that's the model I'm going to test. So here are three quarks. Two of them are spinning this way, and one am spinning that way. That gives the proton a spin half. I put the whole thing in a magnet, and I make it longitudinally this way. Then I let the muon or the electron come through, exchange with the photon, the virtual photon in this case, yes? And then that is a spin 1 that is allowed to interact with any of these quarks, Now, when it's a spin 1 particle, when it hits a quark spinning the opposite direction, it will flip its spin. But the total spin of the whole thing will still be half. The quark spin always has to be half, remember? Always, it's a fermion, yes? It has to be half. So in this case, there are 2/3 of the probability of this flipping inside, yes? Because there are 2 out of the 3 quarks can flip. What happens when you have this third quark which is moving already or spinning already in that direction? In this case, the interpretation of the Gedanken experiment is that it will not interact at all. The spin is not amenable because you cannot have a quark with 2 spin, yes? So that's prohibited. Now, I say, then okay, I can do this experiment and I'll see a result 2/3 of the time, yes? Because 2/3 of the time, one of the quarks will flip. 1/3 of the time, it will not flip. That means the photon will not really see something. Will not be able to see the flip of the proton as well. Then I put the change in the magnetic field, and now the magnetic field is completely opposite. I turn it around, and if my theory of origin of spin coming from quarks is correct, then all the quarks inside them are flipped now. Now 2 are interacting this way, and 1 is interacting that way, or rotating that way, and now the flip is only on one side. So it's 1/3 of the chance that the photon will flip the proton, the quark spin, and 2/3 chance there is 0 chance, it will not flip. So now I know that if my theory is correct, the difference between the two has to be 2/3 minus 1/3 divided by 2/3 plus 1/3. I know exactly what to expect. And we did this experiment with this alignment, and we flipped the spin, we measured it again. To our surprise, this came out to be completely wrong. In fact, the first results were this asymmetry that I'm plotting was 0, with a large uncertainty. Eventually, we figured out that the uncertainty could be reduced, and we learned that only 15% or 30% or 25% of the total spin of the proton was carried by the quarks. Yeah? That was a big surprise. That means that the alignment of quark doesn't work. Something fundamentally is wrong with our understanding of strong interactions. So that was our first result, called the spin crisis at that time, by New York Times and London's Times. And then over the next 50 years, we are doing the same experiment at the relativistic heavy ion collider that exists already, where we are doing the same things with the gluon spin. Over 20 years now, we have figured out that the quark spin and the gluon spin is approximately the same, but they explain only about 30% or 50% of the total spin of the proton. We're looking for a proton spin to be half. This comes out to be about 0.12. This comes out to be about 1.12. So only half of it is explained. So where is the rest of it? Well, we know that at any finite temperature, these quarks and gluons have to be moving along. They can't be stationary. And that's what is giving them what you intuitively would call orbital motion. And that's something that we would like to measure in the future. That they have motion within the proton, and they have to be returning, because the quark is not allowed to leave the proton, which means that at the edge of the proton, it knows that it has to turn around. If there is a turning around and it has transverse motion, well, there's only one type of motion that is circular that allows you to do it, and that's the physical intuition of having an orbital motion to these quarks and gluons. How do we measure it? We'll show you how to measure that. So we need a collider. And a collider, I guess everyone knows, two oppositely charged rings moving oppositely, and then you do collisions at different places with the appropriate wavelengths that we want to see. Coming back, now you have the intuition, right? Now you have the intuition. Now you build it up. I have given you the intuition. So now you don't even need anything, you just know. But the problem about protons in 3 dimensions is where we don't know much. We don't know much about the transverse motion. We don't know about the transverse orbital angular momentum. We don't know anything about it other than the size, which we have measured for many years by scattering electrons of it. If that is the case, we know the proton looks like this. By looking at this, we know it's a human being. That's the knowledge of proton we have so far. But we know that the real might be different. And we have to go from this 2-dimension to 3-dimension to figure out the spin or the orbital motion, because that requires you to go to the 3rd dimension. Without that, there is no rotation. Remember? Think about it. You can't have rotation. You can have simple harmonic motion in 1 dimension, but not rotation. So if you believe in orbital motion, 3-dimensional aspect of the proton structure, you have to know that we have to go further and really go and respect the proton as a 3-dimensional object. And that's what we are going to do. The problem is we have no intuition. We have no knowledge as to how it looks like, and that's where the problem comes. Now you tell me what that is. No, shh. If you know it, just keep it. Anyone knows? Oh, he knows. Okay, keep it. But the idea is clear, right? Now it is more difficult. When you have no intuition, he knew I was from America, from New York, and the easiest thing to do for me is to look at the Statue of Liberty. Everyone knows Statue of Liberty, right? But this one is difficult, and because you don't have any intuition, it's very hard. That means as theorists and experimentalists, I cannot do extrapolations from my existing knowledge or do calculations, as I was mentioning to you, because gluon calculations are very difficult in QCD. Yes? So now let me see if you can guess this. Raise your hand if you can guess this. Don't tell me the answer yet. Okay, 1, 2, I see 2 hands, 3 hands. No? Yes? Oh, okay, sorry. Okay. Now, more hands. More hands, yes. So this is Persistence of Memory by Salvador Dali, right? This is completely unintuitive. This is not how word looks like. And that's why I chose this, because we don't know much about the inside of the proton, how it interacts. And if you don't have interactions, intuitions, you cannot extrapolate. You cannot assume things to be right. You rely on the theoretical models or calculations, go in and then check it experimentally. Only that will work. And that's the idea behind what we want to do. So now we want to look at the three-dimensional structure of the proton. So let's look at this. The assumption is it's a three-dimensional picture. So there is a center, assumed center. There is a quark or a parton here. It has a momentum fraction of x compared to the proton's momentum going in that direction. It has a transverse momentum kt, which has 2 dimensions, up y and x. So it has 2-dimensional x. It has the bt, which is the position dimension. So it's a 5-dimensional object. And you start saying, oh my God, it's going to be complicated. Well, this is called a Wigner function. Nuclear physicists, experimental nuclear physicists, atomic physicists have been using it forever. We did not appreciate that the technology, the detector and accelerator will reach the level that in your and my lifetime, you will be able to see the 2-dimensional structures inside the proton, including their motion. Yeah? But we are reaching that level, and that's what we are actually using to go inside. So I do a simple experiment. I do an electron scattering. This is a photon exchanged, electron scattered, and the quark was rotating this way, and it hit here, and because of the relative motion of this, that direction, and that quark now leaves its path and starts coming out in that direction. At the edge of the proton, it knows that it can't go alone outside because quarks are not allowed to be alone outside. They pick up an antiquark and become a pion in this example. So now, I have shown you a mechanism for creating a pion going in one direction. Yes? For every quark that is rotating in that direction, if it gets hit, the pion will necessarily come on that direction. It turns out that experimentally, we have done this experiment over 20 years, and all pi pluses, always come out on the left-hand side, as shown here. But amazingly enough, pi minuses, which come from the d quarks, they always go on the wrong side, meaning the right side of this picture. So a similar picture for a pi minus looks different. So imagine, we have a u quark going in some direction, and the d quark seems to go in the opposite direction. Did you know that inside the proton? And this has been confirmed over 25 years now. Every experiment, every energy, does not matter what energy you look at. You can do it at 2 GeV center of mass energy or 200 GeV. Every time we see this result, we don't understand it, other than a simple fact that the orbital angular momentum, the u and the d, are opposite. Now, ask my theorists to explain that model. Right? It's difficult. Now we want to actually measure it. We want to go in, confirm this with extremely high precision if it is true, and then try to build QCD-based theories to explain that. So if you really did this, this is the kind of simulation you would get. So this is a higher statistics simulation where the kx momentum of the u quark in a transversely polarized proton looks like that. And you see that it is completely non-zero in that direction. In the y direction, where there shouldn't be any differences, it's 0. If this is true, wonderful. But if not true, we'll want to find out using that future collider. Now, the second thing, I want to understand the position. I will not go into, I promised him I will not use any equation, so I'm not going to show you that. But I'm going to show you something. You think about this. How many of you know baseball or cricket? Baseball, cricket? You only know soccer here, right? I know, well, okay. Well, baseball or cricket have a bat, and you hit the ball with it. Now, I'm going to ask you to make a Gedanken experiment again. A glass bowl with a lot of water in it, and 3 ping pong balls, and the whole thing is moving. And if I give you a bat and say, tell me what the orbital motion of these ping pong balls was. If you take that bat and hit the whole thing, it's going to break. And that means that the motion that you're trying to measure will stop to exist because they'll all fall down. So that is not a correct experiment to do, to measure the motion of the quarks inside. You need to be more careful. You have to be non-violent. Non-violent processes to go inside the proton without breaking the proton. Because you have to go in to interfere with the quarks or the glue. So you have to go with a smaller wavelength. But small enough energy should be there, transferred, that it goes in, but still doesn't break it. Until 2000, 2001, we did not even know such a thing existed. It was an accidental discovery on our experiment at Zeus and H1 that both saw that 7% of the time, the photon goes in, the electron gets scattered, but the proton does not break. It was a completely accidental discovery. Then theory friends like Shandong Ji told us, oh yeah, it should happen with a small 7% probability, and we were getting the exact same cross-section. But anyway, I'm going to use that method now to measure this future thing. Because it is non-violent, I grew up in India, and I now live in the US. So non-violence means these two people. So I always call these kind of collisions non-violent collisions or Gandhian collisions. Bring some history and culture to physics, yeah? So what am I going to do? I want to do this experiment without breaking the proton. So I scatter the electron, the photon goes in, the virtual photon goes in, a real photon comes out, a proton is unbroken, just slightly deviated from its original path. That's what we saw at Hera. Okay? We saw this without understanding what was going on. So it was called deeply virtual Compton scattering. And you could also create a vector meson if something inside, instead of a quark, there is a gluon interaction there. What is really going on is this. So the quark inside the proton gets excited by this virtual photon. Then it de-excites by giving out a real photon. And of course, because of that momentum exchange, the proton still remaining intact, but change in the momentum. So a collider beam coming through and moves a little bit. The angular diversion is so small that you need detectors which are far, far away. And we didn't know the existence of such a process, so we did not have detectors in the very, very far region. But once we understood this was going on, we hurriedly went in and put some detectors in the front, and we saw the signal for the proton. That's how we convinced it. But it was a small acceptance, very bad experiment, because we didn't plan it. We didn't know it. Now we know, if we want to measure it in the future, we better have it. And so the next EIC, the electron-ion collider, we have a beautiful presentation of the layout of the forward region, where we will measure this extremely well. So between the two of them, you will start making these kind of pictures. This is the momentum picture. This is the position picture that comes out of the analysis of the small change in the proton direction. Yeah? That's how you're going to do it. So once you know the momentum and position, R and P, R cross P is angular momentum. For every value of X that you will measure this, you can put the whole thing together to really structure it together. So summarizing this part, you know this is what we did in the past. I argued for this, but I'm going to do actually even more. I don't know why there are pictures of MRIs of watermelons on the internet, but I'm using them to make the case, yes? This is what I will be able to do to tell you what is the structure and the motion of this inside. Similarly, for the mass, total mass has to be related to the quark energy, the gluon energy, the chiral symmetry breaking, the origin of mass, the Higgs boson. But then there is a term that comes from the fluctuations of the gluons. And that's very difficult to calculate. There is really nothing that we know that how it can be calculated, because it's all glue-glue interaction. And that is the difficult part, which we can measure at the EIC directly and then interpret it in certain ways. And that's another part of measuring J size and upsilon production near threshold, meaning at the center of mass energy or slope cross-section, where the center of mass energy just creates that particle, has no momentum, and then it let it decay. And then we measure all of that. And that has connection to the gluon's contribution to that. Currently, the estimates are very, very bad, 20%, plus minus 20%, but this is something that people would want to measure to understand the mass, the origin of the mass. Last but not the least, for the physics type, what does the proton look like at stationary? So I have a cartoon of the proton with 3 quarks and the gluons, and that's the time axis. This is not to be considered as the quarks coming out of the proton, it's just time going in the x direction, okay? Just make sure that I understand. This is a bad cartoon on my front, but that's what it is. It's just the timeline. So what happens to these quarks? They emit these gluons inside the proton, and they come back and fall back again, and they exchange gluons. And here is the place where I zap them with the electron and look at what the cross-section looks like. And if you ask me what a proton looks like at this stage, I will say, oh, proton looks like 3 quarks, 1, 2, 3, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 gluons. That would be my experimental observation in that Gedanken experiment. Now, if I accelerate this proton to very, very high energy, there you go. Now I have an accelerated proton in the accelerator, and the way I am going to show it is that it is Lorentz boosted proton, Lorentz contracted proton, and the same thing happens. However, now you see that the parton fluctuations are time dilated in the strong interaction time scales. So what does that mean? You know that now it is moving at 0.999 speed of light. It means that all the things are slowed down. If the time is slowed down, these photons which are created have more time to fluctuate into 2, and the 2 can go into 4, and 4 can go into 8. Remember that gluon coming from quark coming from infinity to your lab. That same thing now is going on, but now they have more time to do this. Yes? More time means more gluons can be created. So that's the simpler explanation why you see for the same time zap, more gluons seeing here at high energy. That's one way to look at it. So the long-lived gluons radiate further small gluons, which in turn radiate more, leading to a runaway growth. This has been already observed at the previous collider. At Hera, we have actually seen a growth of the gluon distribution. Every one of you who is working in high energy, in CMS or Atlas or wherever you're working, you have used this part in understanding the parton distribution function. That measurement of gluon distribution comes 20 years ago from the Hera experiment. And what it shows us actually is mentioned in that Nobel lecture by Origin of Mass. Result is a self-catalyzing enhancement that leads to a runaway growth. A small color charge in isolation builds a large thundercloud. Yeah? That's the reminder I had for you before. And the simple process that he says this happens through is this. And he says this can go on forever. That's the thundercloud. But is it true? It can't be true. Nature is finite. Everything is finite. It can't be infinities, only in theories, right? So what's wrong with this picture? The Nobel Prize talking about this. The picture is wrong because it is not in isolation. It's inside a proton. So there's a finite volume, which means that the gluons have to be inside all the time, which means that crowded gluonic matter starts not only growing as it was, but once it is too crowded, the two adjacent gluons will merge. They are colored particles, they will merge. So the crowd grows, and at some point it becomes saturated. No more gluons are created because effectively more are created, but the same number are merging back into 2. Yes? So that the growth and the merging become equal at some point, and that's where it forms something of a unique state of matter. It is completely gluonic in nature. You have never seen such a state of matter experimentally. Yes? It is completely gluonic. It's no quarks play very little or no role in there. And that's what we are trying to understand. If that happens, because the QCD tells us this has to happen, but we have never seen it for reasons that I will not go into right now, but that's the saturated state of matter where this becomes equal, and it has properties which allow us to call it color glass condensate. It's colored because the interactions are colored, condensate because they're spin 1 particles, and glassy because this forms a viscous liquid or viscous, whatever you want to call it, that is continuously covers the entire volume of the nucleus or proton, whatever you're looking at. Yeah? And it should be universal according to QCD. We don't know whether it is there universally. At high enough energy, CMS has a fantastic paper about collective behavior of proton-proton collisions at extremely high energy. This was 2012, something like this. Yeah? That's one of the fascinating papers that tells us that there is something unusual there which is going on, because in the proton, nobody expected such things. Collective behavior of partons. Yeah? That was the first one that discovered it, and I remember reading it with great fascination. So here is what we have done. We have done electron scattering at different energies, discovered many things, and earned lots and lots of Nobel Prizes. What we are now going to do is to go into the nuclear era, look at the proliferation of gluons, and really figure out whether there is such a thing like the gluon saturation. That's the third prong of this. And last couple of slides, I want to show you how we are going to do it now. So we have this collider already. We have something called relativistic heavy ion collider, which is at Brookhaven National Lab. That's the complex of the Brookhaven lab. And you can see it's a 3.8 kilometer collider. You can see it from the top. Unlike LHC, it's not deep on the ground, it's on the top. Yeah? And all of the injector chains are shown here. The beams start there, going to something called the booster, then the AGS, and then goes into the RIC collider currently. Yeah? And yeah, it will conclude its operation in about 2025, next year, and then the installation of the electron ion collider starts in the same tunnel. So we save a lot on the construction of a tunnel by making use of all the things that are there. We estimate that about $2.2 billion is the replacement cost of RIC today. And so all of that is assumed in the cost estimates that we have. What will happen eventually is that this will look like this, with the electron beam coming from here and then going in anti-clockwise direction and colliding with one of the existing rings. We'll take one of the rings out and then have a collision in the two experimental areas. This is called the 6 o'clock, which is where some of our colleagues called STAR collaboration sits, and this is the location of the S-Phoenix or Phoenix detector that existed before. It will be the world's first and the only polarized electron, proton, and light ion collider. It will be the only electron nucleus collider in foreseeable future, and uses all the things that we have already used. And this is another view of it. You see that this beam comes through, electrons go this way, the hadrons go this way in there, and then they can collide at two different places. The detector looks like a collider detector. Technologies are the same, so if you are working on CMS, Atlas, anything in high energy physics, you are transparent. You will actually build, we have research R&D projects which are funded through the CERN and US DOE, which are commonly funded for both purposes, both upgrades at LHC and the EIC. So the technologies are very similar, your philosophy is similar. There's a very thin silicon tracker that sits inside, then followed by particle identification systems, which were uniquely different than the high energy, but they are needed in our physics. Then you get into the magnet, then the electromagnetic calorimetry, and finally the hadronic calorimetry. So you can see this as a function of radius. It looks very similar. That is summarized here. We have a 2 Tesla superconducting coil magnet which is being built. But one thing I want to emphasize is that this 9.5 meter beast sits right there. The rest of this is accelerator ring that both beams are carrying. But because of those small angle deviations that we want to measure, our detectors go all the way to 50, 60 meters away from the center. And those have to be assigned now before the design is complete in the accelerator lattice. So that has been the biggest effort that people have made in the last few years to make sure that you don't lose on any properties of the beam that we want, at the same time get the acceptances that we want to see the physics that we want to see eventually. It's an international group, and you can see the different flags of different countries. Of course, each one of them has US involved in some way or the other, so the US flag is not shown on this plot, but you can see it's a real international effort. So the user group that we have formed to work on this is about 1,450 PhD members from 40 countries and about 290 institutions all over the world, a mix of particle and nuclear physicists who are working on the cusp of things that you can see here. And this is the split, about 32% Europe, 45% North America, and about 20% Asia, with a small African and South American contribution, which are growing, and I think Europe is also growing, Asia is also growing. I think the US part is saturating quite fast unless high energy physicists are going to start joining. So I think the nuclear physicists are there. Let me go further. I want to summarize with what we know about the proton through this beautiful new simulation that we did that came out from Jefferson Lab and MIT collaboration. What is shown here is a Q squared of 1. Remember, Q squared is small. Q squared is small. Momentum exchange is small. Wavelength is large. That's not a good idea for deep inelastic scattering, right? Remember, the lambda is equal to h bar by p. So small means lambda is large. If you keep that condition, what do the parton distribution functions mean in terms of seeing things? Is shown with the resolution that is shown there. Yeah? Now let's look at that. See the mouse? Where? Where is the mouse? Oh. Oh, no. Oh. Okay, here. So we are looking at the proton. It looks at Q squared of 1 and an x of 10 to the minus 4. Now we are at 10 to the minus 2. At Q squared of 1, the proton starts looking like this. At very high x, if the resolution is not good, you still don't recognize your proton. That's the reason why you want to go to a higher resolution probe. And we will go there now in the next part, which is high Q squared. That means smaller lambda. Now look at it more carefully with a high resolution. Suddenly at 10 to the minus 4, you see all that beautiful C quark, C glue. Now we are in the intermediate. It's a mixture of quarks and gluons. And now it will move to the high X region, and you suddenly start seeing the 3 quarks. Yes? So 100 years of physics has taught us this is what is going on. Yes? Only in the unpolarized regime. We don't know anything about what happens to the spin. What does spin do to this? What happens to these structures? Why the U quarks go in one direction and the D quark go in the other direction, for example, just by putting this thing in the magnetic field. Yeah? We don't understand that. And that's sort of something we're going to solve, or at least try to understand as we go further. So that's the summary. In EIC of science, understanding protons' mass and spin and those gluonic interactions. We would be able to show the origin of spin and mass with simple simulations that I just showed you before. We cannot do that right now. We cannot do those simulations that I just tell you. That has real physics in it based on all the Hera data and proton-proton scattering and everything that we've seen so far, these PDFs which we've used. But the gluon, the spin part, we cannot do. We'll be doing it after we have this data. You can go to this website and get yourself amused by a lot of other things that are there. You want to put it in a perspective. From the Big Bang, this is where things began. The accelerator started taking data here. Rick and LHC sit somewhere there. And then what we, at the EIC, we start at the same place. The proton structure, proton structure emerging from the quark-gluon interactions, and go this way to see how light nuclei are formed and the heavy nuclei are formed. Basically, go from places where you create the quarks and gluons from the energy and move into how they hadronize, how they fragment into various things. So that's the perspective with which I want to leave you with. The project is just beginning. It's the right time to jump in. The science is of gluons and a super God particle. It binds us all, creating 98% of the proton mass and possibly a significant part of the gluon spin and all other properties. EIC project has a significant momentum on all fronts right now. The science is compelling, fundamental, and timely. The construction starts in 2025, and first collisions expected around 2031. Physics starts about 2 years after that. The detector has to be ready in 2031 because when the machine starts, we want to give feedback. We want to make sure the detector works. So that will be a time of about 1 year, 2 years, something like that, where the machine is learning how to run, and that's what we plan to do. Last is, there you go. It's exciting times ahead, and it's really the machine and the program for those who are younger than me. So, thank you very much, and thank you for inviting me again. Went over time.
Thanks, Abhay. Perfect on time.
Okay.
Really, very well scheduled and programmed.
And I'm sorry for using 2 equations, not 3 equations.
I think this audience will, will forgive you. So questions, guys?
Let me break the ice. While people think of the questions, I have a comment and a wish. The comment is something that you didn't tell about, which is that you have a detector that is red blind. Right? So you want
a detector is various?
that is daltonic, it's red blind.
Red blind.
Yes, you have a watermelon and you can only see the seeds.
Ah, okay.
Because you're using an electron beam.
No,
Yeah.
no, that's wrong. I will tell you why. Because the photon, I actually measure the gluon much better than anything else because photon creates QQ bar pairs inside and they interact with the gluons. That's why the best measurement of the gluons does not come from PP scattering. It comes from HERA. EP scattering, 20 years of history, which is not known.
But that's already a virtual meson hitting the... So you're fluctuating, say, to a J psi, and you're really doing...
Not just pi,
scattering.
no, not necessarily. Yeah. It's just simple glue created at the, inside, right? You need a QQ bar pair, that's all you need. You don't need to have a quarkonium. You don't need to produce a bound state at all. You have lots of quarks, anti-quarks created just because the photon is splitting into it. It's simply, it's not quarkonium physics only. It is also, but it is not only.
Okay.
And that's why HERA has measured this better than anything else. The most precise measurement of the gluon distribution comes from HERA. This is EP scattering. And we are going to do the same thing with 1,000 times more luminosity with not just the proton, but also with the nuclei. So there is no limitation at all. In fact, the alpha S is stronger. Alpha E times alpha S is overcome by the 1,000 times more luminosity.
Okay, and then the wish.
So we are actually not blind to at all. We are actually very focused on that.
Okay. And then the wish is if you could show sometime a scaling plot for exclusive processes. Because I haven't seen the equivalent of the deep inelastic scattering scaling, which is beautiful, for exclusive things. So to establish experimentally that the GPD factorization theorem is...
Agreed. So this will be part of the physics program as we started. Absolutely. So everything, so the philosophy always has been to establish something in the cross-section, understand its complete exclusivity in this case, understand its factorizability, and then apply the theory to interpret the results. So this has been the case with PP. Fortunately, the history at RIC is that way. So we are going to continue that doing in the EP as well. And you're absolutely correct, we'll need to do that. No question. But that's even a good challenge for theorists because they are also looking for factorization No, but factorization, not every measurement has been shown to be factorizable so far. So they have to also show us that that's happening. If it is not happening, we learn something new. If it is happening, we use it to go next step. Yeah.
Thanks for the nice talk. I was wondering on possible synergies, overlaps, competition with CBM at FAIR, Compressed Baryonic Matter program?
For the CBM FAIR, I can't really tell you directly because they're looking for mostly, I mean, correct me if I'm wrong, the groups that I'm aware of, they're looking for the transition between quark-gluon plasma. So here we are not melting nuclei. We are taking the nucleus that actually melts later, trying to find out what is the initial state, right? In RIC, we have nucleus, we melt it, we create the quark-gluon plasma. We try to understand the physics of it, and then we say the biggest uncertainty comes from the fact that I don't know the parton distribution of the nucleus. I'm going to give you the best parton distribution of the nucleus. In fact, she's going to give you the best parton distribution of the nucleus. She's the expert on it, right? So that's what we are going to give you, yeah? But the melting of that part, the critical point measurement is not. However, there is a panda. The FAIR has a sister, future panda. That has spin associated with it, with protons and antiprotons. We can do there. We can collaborate very much on that front. Very much on that front. Oh.
Still under control.
Sort of prompted by that. And what about the complementarity? You know, there is, would there be complementarity with FCC-EH, which is potentially one of the phases in the future?
So I can tell you why EH, right? Everything in LHC and FCC also has complementarity. For example, when you look at your signals for beyond the standard model, you have to subtract all QCD out. Where is the largest uncertainty? When you have the LHC upgrades, luminosity upgrades, the largest uncertainty in the subtraction of background will come from the gluon distribution uncertainty that comes from Hera. And I'm not even telling you speculating, I'm telling you the fact. We have workshops which are going on LHC and EIC right now. We have determined both for Atlas and CMS, the largest uncertainty after luminosity upgrade is going to be limitations that come from Hera. And I'm telling you that we'll measure at least 5 times better than Hera. So the smallest beyond the standard model signals that you need will be coming from this machine because we will measure it from day one. So inclusive, right? Now let me go to the next level. So the next level is, let's say, leptoquarks. Backgrounds of those we will measure complementary to Hera and LHC. Yeah? Because you'll be measuring them at some much higher dimension, energies. We have regions in which we believe we can measure. Third thing we can measure is E to tau lepton flavor violation. Not E to mu, because simply the backgrounds overwhelm us. Because there are dedicated experiments to do E to mu or mu to E. Those experiments will do much better than we can do. But for E to tau, there are not too many experiments in the world. Yeah? So those kind of things, which are niche high energy physics interests, we can do.
So I was thinking more if after, so FCC-EH, so that would come after this. So
yeah, okay. So EH is very dedicated, yeah, it's a directly same physics. Here, the difference is FCC will never have polarized protons. Spin is not there. But you will have beautiful, extremely high energy protons and extremely high energy nuclei if you preserve that ability. And then you can do the low X physics, the color glass condensate physics that I told you about, saturation of gluons, absolutely beautifully. Absolutely beautifully. In fact, there is a project currently, people think about LHEC. You heard of that?
Yeah, I went to the FCC. But
exactly.
That is,
so that is complementary, exactly complementary to the same way. Yeah? It will be a beautiful low X physics machine, no question about it. But we don't see that it will happen before EIC. Yeah. But it will be complementary, absolutely.
Okay.
Thanks. So just a comment to possible connection, maybe naive connection to FCC AH program. The things that we know that in general, for example, Higgs production is an excellent channel to probe glue on TMDs, for example.
Yes, of course, glue, yeah.
I imagine that even if we are at very large energies like the FCC, if we measure the Higgs rate, the transverse momentum rate at low PT, this distribution, we still are able to measure the TMD distribution, the unpolarized.
That is correct.
But also the longitudinally polarized, because even if in this case we have just one proton beam, if it is unpolarized at low PT, we can access the intrinsic polarization of gluons inside the unpolarized proton, which is something that I believe that could be feasible even at 100 TeV nominal.
I know
energies.
from the theorist point of view it is visible. From the experimentalist, I need to know what the signal is and how large it is going to be.
But we have ears.
But yes, we have a common ear there, absolutely. I saw, did you want to ask something? Or no? Here.
Talking about complementarity, so what is the present state of second detector at AIC?
So currently, the money that has been assigned to us includes money for machine fully, 95%, and we expect that 5% is coming from international collaborators and partners. For the detector, we could have done it differently. We could have said whatever money we have, we'll split into two, and then start building 2 detectors. People at that time felt that that was too ambitious to have enough. We didn't know exactly how many non-US groups will join. So we decided that we'll be a little bit more conservative and start building the first detector. And so the idea is that the collider has capabilities of 2 collider halls. We are preserving all of that. The design of the first detector is well, and the machine is well on the way, as construction has to start next year. But once that starts, we want to make sure that the second detector effort starts. My expectation in a best case scenario that the second detector will come about 5 years later. Now you might say, hey, that's a problem. No, it's not. D0 and CDF were exactly 5 years later. And if you talk to them, now you look back and they look at the results, they're no different. Impact of the results were no different. Why? Because any collider takes some time to turn on and get to the machine, best possible operation conditions. So CDF came first, the accelerator started, made lots of mistakes, burnt a lot of detectors, and then they learned how to build it, how to run it, and 5 years down the line, there were no mistakes. D0 came along, no detectors were burnt. So my hope is that we'll do that way. But that will take a large effort from non-US countries right now. At least for now we see. But it is essential because some of these important results have to be confirmed not with an identical detector, but technically complementary detector. We have to look at results from different philosophies in the sense of the analysis philosophies of the 2 detectors can be different. As you know very well in CMS and Atlas, they are complementary. They think differently and design all of that has to happen. So some of them will be common, important results, they have to be double-checked, but there has to be some new physics. And this is where the exclusivity comes in. My hope is there are some very clear differences in the interaction region of the 2 collider detector halls. One is a crossing angle of about 35 milliradians. The other one is at 55 milliradian, 50 milliradians, or 25 and 50, which means that the nucleus that comes from one side and the electron that splits it, in the very forward region, you have more space in the second detector to detect all the fragments. So for all the kind of tests that you suggested, for exclusivity, the second detector is a better detector to do. Not that the first one is bad, it's better than anything that anyone has done in the past. But I bet we're going to find something that is interesting, and then we're going to go after that part. I mean, I remember in 1999, I had a conversation with Veneziano at CERN, and he told us that we need to look at the target fragmentation. He had these ideas about fracture functions, not structure, fracture functions. And he was talking about it, and we were saying, what do we do with this? We are doing fixed target experiments. You can't look at the fragments. But he said, no, go to the collider and do this. This is important. And we are going to make that dream true. We are going to make that dream true because he asked us to measure lots and lots of things in the fracture region, very forward region, fragmentation region. And we are doing very well in the EPIC. But I believe if we pay close attention to that, we're going to do even better in the second one. Yeah?
Thank you.
And one more comment is that muon detection capability doesn't exist in EPIC. That's because we didn't ever ask for that. But every time I talk to my high energy colleague, they said, what about the muon? So here is your challenge. Second detector, muon collection. Really, really good. We would be glad to have a big group with experience at CMS join us with that. Yeah? So this is really something that you should look into. Absolutely. And look for EIC, LHC synergy workshops. I think the first one we had it at CERN, second one in Belgium last year, third one I'm not sure where we are, but just next time you hear about it, pay attention.
Some more questions? No, I think that's enough for today, and a very wonderful talk. Many thanks.
Thank you, thank you. Thank you for having me.
So as Abhay said, he's here today, probably, I don't know how long. If any of you has some further question, just come down and we can have a chat. Thanks.